All right, so that brings us to letter B. Integral x squared over x minus 1 times x squared plus 2x plus 1. So the first thing to recognize is that x squared plus 2x plus 1 is quadratic. However, it is not an irreducible quadratic because you can factor it into x plus 1 squared, right? All right. And by the way, the degrees of the numerator and denominator are okay. The top is degree 2, the bottom is degree 3. So this is a proper rational expression. So we can go ahead and set up our partial fractions. Again, we have all linear factors. However, this time one of them is a repeated linear factor. So this is going to go a over x minus 1 plus b over x plus 1 plus c over x plus 1 squared. Okay. All right, so now we'll clear the fractions. We have to multiply both sides by x minus 1 times x plus 1 squared. This is one of those times when I miss being in an actual classroom with a real whiteboard because I'd have a lot more room to write this, right? Wouldn't have to squeeze it in like this. So on the left side, everything cancels. X minus 1 cancels, x plus 1 squared cancels, and just leaves me with x squared. On the right side, I'm going to distribute. In the first term, the x minus 1 cancels and leaves me a times x plus 1 squared. In the second term, one of the x plus 1s cancels, and one is left. So there I'm left with b times x minus 1 times x plus 1. And then in the third term, the whole entire x plus 1 squared cancels and leaves me c times x minus 1. Okay, so in any case other than distinct linear factors that all have degree 1, my shortcut does not work completely. However, it's still usually helpful. All right, so for example, one good number to knock out some stuff is x equals 1. I see that's going to wipe out the b term and the c term, and it'll tell me what a is. So that's going to give me 1 equals a times 1 plus 1 squared is 2 squared plus b times 0 plus c times 0. And that means that 1 is equal to 4a, which means a is 1/4. All right, so now let's see, x equals -1 should be kind of helpful. All right, if you set x equal to -1, the left side is still 1. The square of -1 is 1. And this term drops out, and so does this term. This is going to tell me what c is. C times -2. All right, so it looks like 1 is equal to -2c, which means c is -1/2. All right, so the only thing that my method will not come right out and tell you is the value of b. So now just pick some other number. Unfortunately, we've used up all the numbers that are going to make whole terms drop out. So just use the nicest number you can think of. For example, x equals 0 is usually pretty nice. So let's see what happens when we set x equal to 0. What that should give us is an equation that has A, B, and C in it. But we know the value of A and we know the value of C, so we can figure out B from there. So if we set X equal to 0, we're going to have 0 equals A times 1 plus B times -1 times 1 plus C times -1. So 0 equals A minus B minus C. And we know A is 1/4. We know C is -1/2, right? All right, so that means that 0 is equal to 3/4 minus B, which means B is 3/4. All right, we have all of our mystery coefficients. So now we can evaluate our integral. The integral of x squared over x minus 1 times x plus 1 squared is equal to, and now, especially since these are fractions, I'm going to write them outside, 1/4 integral dx over x minus 1 plus 3/4 integral dx over x plus 1, and then minus 1/2 integral dx over x plus 1 squared. All right, so the first one of those and the second one of those are natural log. Those are basically du over u. So this is 1/4 natural log absolute value x minus 1 plus 3/4 natural log absolute value x plus 1. Now, the last one is a little different. Please, please, please don't tell me that's minus 1/2 natural log x plus 1 squared. All right. You want to think of this integral as integral x plus 1 to the -2. And that's just going to be a backwards power rule. All right. The integral of x plus 1 to the -2 is x plus 1 to the -1 over -1. Right? Okay, plus C. All right. So that is going to give us plus 1/2 times 1 over x plus 1. And so that particular term does not get a natural log. And then, of course, no points if you don't remember plus C. Just kidding. All right, not too bad, right? Maybe just a little tedious. Definitely doable. All right, so that brings us to this little monstrosity. If I remember correctly, this problem takes a little bit of time. This is letter C, by the way. All right, so what we have here is an irreducible quadratic. 4x squared plus 1 cannot be factored using real numbers. So this would be a case of where we have to break it up like this. So we put an ax plus b over 4x squared plus 1. And then we put a cx plus d over 4x plus 1 squared. All right, so unfortunately, my shortcut method does not really help with this situation. However, I am going to start the same way as always. I'm going to clear the fractions. So let's multiply both sides by 4x plus 1 squared. All right, so on the right-hand side, those just cancel and leave me 8x squared plus 8x plus 2. Then I'm going to distribute 4x squared, 4x plus 1 squared. In the first term, one factor, 4x plus 1, 4x squared plus 1. Sorry. I usually write it correctly, but sometimes say it wrong. All right. So this is going to be ax plus b times 4x squared plus 1. And then in the second term, the whole entire 4x squared plus 1 squared drops out. Okay. So here we go. Let's see. Just thinking about how I want to do this. I think I'm going to do this the same way that Show Me an Example does it, just so that you've seen it done that way once. All right. So what that involves is multiplying out all of this stuff and writing the terms in descending powers of x. All right, so let's see. That's going to give me 4x squared times ax is going to be 4ax cubed, and that's going to be the only cube term in this whole thing. All right, then we have a 4bx squared, and I believe that's going to be the only x squared term. All right, so we've taken care of this, we've taken care of this. Now when I multiply these two together, that's going to give me an ax, which can be combined with the cx. Remember, we're writing descending powers of x here. So I'm going to write this as a plus c times x. And then the constant term, there's going to be a b and also a d. So the constant term is b plus d. All right, so remember what I said earlier. This equation is true for all values of x. And when you have two polynomials that are equal for all values of x, what that means is that they are the same polynomial, which means they have the same coefficients. Okay. So for example, the x cubed coefficients are going to be the same. And the x cubed coefficient over here is 0. So that means that 4a is 0. The x squared coefficients are the same, which means 4b is equal to 8. The x coefficients are the same, which means a plus c is equal to 8. And the constant terms are the same, which means b plus d is equal to 2. All right, I'm glad I did it this way. Actually, in this problem, this way ends up being a lot easier than the other way that I might have done it. All right, so if you look at those equations, what we have is a equals 0, b equals 2, right? C equals 8. And then if b plus d is equal to 2 and b equals 2, that means d equals 0. All right, so taking our values of a, b, c, and d, this is what we have. So I think I am going to separate these into two separate integrals because these are pretty different in terms of how you have to evaluate them. So we have integral 2 over 4x squared plus 1 plus integral 8x over the square of 4x squared plus 1. All right. Well, why don't we start with the easy one first, which is the second one. That's just going to be a substitution. If we let u equal 4x squared plus 1, then du is going to be 8x, almost like it was rigged that way. So this is not an integral du over u, it's an integral du over u squared, which is a backwards power rule. Okay, and we know how to do that. So now let's look at this other one. Integral 2 over 4x squared plus 1. That is your inverse tangent integral. If you have your handout from section 8.1, we're going to use formula number 19 for this one. I am going to write this as two over the square of 2x plus 1. And now I think, just to be careful, I'm going to set this up as a substitution. Let's let z equal 2x. It's technically a baby u substitution, but, and that's going to make dz equal 2 dx, which is going to turn this integral into, I'm being a little sloppy with my notation here, integral dz over z squared plus 1. Perfect. Okay, and then the plus over here. All right. So this is going to be just inverse tangent z, right? And this one here is going to be minus 1 over u, right? Because it's u to the negative 1 over negative 1. And it's not about u, it's not about z, it's all about x. So let's write this as inverse tangent of 2x minus 1 over 4x squared plus 1 plus c. Believe it or not, that ended up not being as bad as I thought I remembered. And I think part of the reason for that is that I had done it my way before, and that ended up taking longer. All right. Okay, so that brings us to our last example, which is integral x to the 4th over x squared minus 1. And the only thing special about this one is that the degree on top is not less than the degree on the bottom, which means this is not a proper rational expression. So the first thing we have to do is rewrite it using long division. So let's take x squared minus 1 and divide it into x to the 4th. X squared into x to the 4th goes x squared. X squared times x squared is x to the 4th. X squared times minus 1 is minus x squared. Subtract the whole thing. Okay, so then these two cancel. I have 0 minus negative x squared, which is x squared. So I'm going to go one more time. X squared into x squared goes 1. 1 times x squared is x squared. 1 times negative 1 is negative 1. Subtract the whole thing. And that leaves me with a remainder of 1. All right, so that means we, instead of integral x to the 4th over x squared minus 1, we want to think of this as integral x squared plus 1, which is the quotient, plus 1 over x squared minus 1. Okay, so now I need to concentrate on this, and we need to break that up using the method of partial fractions. And of course, x squared minus 1 factors into x plus 1, x minus 1, which are distinct linear factors. So we're going to go a over x plus 1 plus b over x minus 1. I'm going to multiply the top and the bottom by x plus 1, x minus 1. And that is going to give me 1 equals a times x minus 1 plus b times x plus 1. All right, so my method will work beautifully for this one. If I set x equal to 1, it's going to give me 1 equals a times 0 plus 2b, which means b is 1/2. And if I set x equal to -1, it's going to give me 1 equals -2a plus 0, which means a is -1/2. All right, so picking up with this integral right here, let's just copy that over. We have integral x squared plus 1 plus 1 over x squared minus 1. That becomes integral x squared plus 1. And then the first term was a over x plus 1. It turned out that a was -1/2. So we have minus 1 over 2 times x plus 1 plus 1 over 2 times x minus 1. All right. So I think we can integrate all that stuff. Integral x squared is x cubed over 3. Integral 1 is x. And then these are both du over u. So this is going to be minus 1/2 natural log absolute value x plus 1 plus 1/2 natural log absolute value x minus 1. Don't forget the plus c. All right. So that about does it for partial fractions. That's going to do it for section 8.5. We'll see you next time.